So thanks a lot for the introduction. So I will talk about abstraction for performance portable weather and climate model. But to begin with, I will explain you why we started this project and why we built the CLAW compiler. It's because we reached a performance portability problem at MeteoSwiss. So it all started when MeteoSwiss decided to port the COSMO weather and climate model to an hybrid computer. They decided to do that for several reasons. They increased the resolution of the model. They went from a single forecast to an ensemble forecast, and so on. So they needed much more compute power, and for that, they needed like 40x the time, the size of the previous computer. The problem is that it was not possible to put a 40 times bigger computer where the MeteoSwiss computer is hosted. It's at CSCS. So they went for an hybrid architectures with lots of GPU. So here you have the 2 racks that are used at MeteoSwiss, both for production and R&D. It's 12 nodes per racks. Each node has 2 CPU and 8 NVIDIA K80 per node. The model was ported fully to the GPU, so it means that we are trying to reduce all the data transfer between the host and the accelerator. So everything is ported, all the data are ported to the GPU at the beginning, then we do all the computation on the GPU, and we copy back to CPU only when we need to do output. The model was ported with different programming paradigm. So the dynamical core was rewritten totally with a C++ library called Stella. So it's the predecessor of the grid2 library for the one who knows. And the rest was all ported from Fortran for CPU to a Fortran code with OpenACC directives to be able to run on the GPU. So if we take a simple example of a physical parameterization, this is some results for the COSMO Radiation. So on the left side, you have the original code that is run on CPU. So you have a certain execution time. And if you put some OpenACC directives in it, then you will get some speed up when you run on the GPU. So this is fine. But if you are restructuring your code in terms of loop structure, you can gain even more. Like we have found that you can gain even like 35% of performance. The problem is that if you take back this code that is restructured in terms of loop structure for a GPU and you run it back to the CPU, then you lose performance. And the problem of weather and climate model is that they are shared between different institutions and universities, and you cannot restructure all the code and push it back to the repository because other users have different hardwares, and probably they don't want you to change because there's going to be a penalty for them to run that on their computer. So if we take a brief look at the loop structure that I'm talking about, on the CPU side for typical physical parameterization in COSMO, you will have a big loop iterating over the vertical levels, and then you will have inside several small loops iterating over the horizontal grid points. So this is fine on the CPU because it helps the compiler to auto-vectorize the things, and you have good performance. But on the GPU, you want to have a different loop structures to expose more parallelism. So the things that you want to do is expose the horizontal iteration because it has more points than the vertical, so you can have more parallelism on this side. And then inside, you will have the vertical loops that in physical parameterization carry dependencies, whether the horizontal grid points doesn't carry any data dependencies. So as I said, weather and climate model are used by several institutes and universities that are running different hardwares. Those are massive code base. For COSMO, it's like 200,000 lines of code. For a global model, it's more than 1 million lines of code. They have usually a really long development cycle. So it's like 10 years or more to develop those kind of code. So of course, it's hard to rewrite them on the fly. There is lots of architecture optimization that have survived along the different generation of computer. You still find some optimization for vector machine that were used 10 years ago that are still in the code, but nobody knows why, so they are afraid to remove them. And of course, most of this code are optimized for CPU because the most users using those code run CPU supercomputer at the moment. And in terms, of course, of software engineering, because I'm a software engineer, there is no or few modarity in those codes. So it means if you want to isolate one physical parameterization in the code, you will end up with half of the code with you because everything is really tied together and it's really hard to refactor that. So until now, the solution was to have a preprocessor micro and have two different code paths. So one for the CPU and one for the GPU, of course, only in the time-critical places. But the problem is that when you have those kind of codes, of course, it's really hard to maintain, it's error-prone. And the domain scientist that is fixing something, for example, in Germany, where they run only a CPU supercomputer, he will not be able to find the mistake in the GPU part, or will maybe not fix it in the GPU part. So you end up with different branches, and each institute that has a different hardware have to maintain this. So with all of this, we ask us several questions. Of course, what is the best loop structure that we need to apply for the next architectures? Do we want to rewrite the code each time we have a new supercomputer? Do we have the resource to rewrite the code? Of course, because like at Metal Swiss, there is only a few people working in the development group. And can we have a different code than the people in Germany running also COSMO and keep up with them in terms of science? And so on. So we came up with our ID, which is the CLAW Single Column Abstraction in what we call the CLAW DSL. So it's targeting physical parameterization in weather and climate model. And the basic idea behind this is that in physical parameterization, you have no data dependencies on the horizontal. So you can compute each column totally independently and in parallel. So with this idea in mind, we decided to completely abstract the horizontal grid points and let the domain scientists focus on the algorithm for just one column or even 1 point in the model, and have a tool that is able to know the target architectures and let the transformation from this single column abstraction to a performant code for a dedicated target. So the basic idea, if you have a code running now without single column abstraction, the only thing that you will have to do is remove all the do statements that are iterating over the horizontal, of course, and demote all arrays that are indicating any horizontal information. So some of the arrays, 1D arrays will become scalar, 2D arrays will become 1D, and so on. And to demonstrate this idea, we have taken a simple example in our paper. So it's the code from Robert Pincus and his colleagues from University of Colorado. It's called RRTMGP. It's a modern radiation code. It's written with Fortran 2003 and 2008 Fortran style. It's really, in terms of software engineering, really nice written. But nevertheless, it's written with CPU performance in mind. So you have the horizontal loops as the most inner loop in every iteration to help the compiler to auto-vectorize. So if we take a brief look at the loop structure of this code, so this will be a really simple snippet of the shortwave solver code. So you have in purple one big loop iterating over the spectral band. Then you have the red loops that carry dependencies over iterating over the vertical. So you will have one upward loop, one downward, and one upward again. And then inside, you have smaller loops in green iterating over the horizontal grid points. And then, of course, inside the loop, the actual computation. So if we move this code to a single column abstraction, what we do is just we get rid of all horizontal information. So we just end up with our spectral band iteration, IGPT, and we have the loop that carry dependencies over the vertical here. As you can see, before we had indexes over the horizontal, but then we don't have them anymore because we don't want the domain scientists to have to write anything related to the horizontal dimension. And then, of course, we need a way to tell our tool that this code is a single column abstraction, and then we have to transform it. So we have a simple directives that says, okay, I have stripped the horizontal dimension, so I define a new dimension that is called the I-col, so the column dimension, and then I go from 1 to the number of columns. And then I instruct my tool to parallelize this. And then the good things with this approach is that we are 100% standard Fortran code. So you can even plug your physical parameterization written as a single column abstraction directly into your model by adding a loop iterating over the column. The only problem is that you will call these subroutines once per column, whether for performance code you will call it once with all the column. But this will be also transformed when you apply our tool. But the nice thing is that you can use this code without our tool, compile it with your standard Fortran compiler, debug it with your standard Fortran debugger. There is no interference in that. So then, of course, we need a tool that is able to understand this single column abstraction and transform the code. So we call it the CLAW compiler. In fact, it's a source-to-source translator going from Fortran to Fortran code. It's based on the OMNI compiler project. I will talk to that in the next slide. We are able to understand Fortran 2008, and of course, everything older than that. It's fully open source, so you can get anything on GitHub, even the directive specification. And we use it for the single column abstraction transformation, but it's written as a high-level transformation framework for Fortran, so you can write any Fortran code transformation with it. So as I said, we are based on the OMNI compiler project. So it's written, it's a project done at Riken RCCS in Japan with the University of Tsukuba. So it's like a set of programming libraries that helps you build source-to-source compilers. So you have front-end and back-end for C, Fortran, and now even C++ with the Clang front-end. And it has a specification of high-level intermediate representation. So you have a really high-level representation called Xcode.ml, where you see all the loops and all the Fortran keywords that you want to understand. They use it to build their own language called OpenMP, which would be one of the languages for the post-K computer. So in our project, we are using the Fortran front-end and back-end, and we apply transformation on the Xcode.ml intermediate representation. But of course, we contribute a lot to this project. We have issued over 100 pull requests so far to the OMNI compiler, and we are talking almost every day with them to improve this project. And to our knowledge, it's the only open source Fortran toolchain with high-level intermediate representation that is able to deal with modern Fortran code like it's found in the global icon model. So as I said, it's more like the CLAW compiler is more like a high-level transformation framework. So we have lots of like transformation primitive, and you can just write a class for yourself to do another transformation and use those primitive and plug it into the toolchain and do another transformation. So back to the example. So we have our code in a single column abstraction. So it's agnostic for any optimization in terms of loop structure. And then we instruct the compiler to transform this code for a specific target, so GPU, CPU, or whatever target we can implement in the backend. And we say, please use one set of directives. So it could be OpenACC or OpenMP for GPU, or just OpenMP for multi-core CPUs, for example. And then our compiler will do the transformation. But what does it do? Then inside we have some recipes that we know works really well in terms of heuristic to transform the code. So of course we do lots of data dependencies analysis to know which variable have to be promoted to fit with the model data. And of course, if we target an accelerator, we have to know what kind of data movement we have to generate in the code. And potentially also we can collapse loops that have no dependencies. Of course, we adapt the data layout, so it means if a variable in the model is a 3D arrays, but in the single column abstraction, it has been stripped down to 2D arrays, we can issue a promotion. We can detect any unsupported statements that will not work with the target directive that we want to apply. If we can, we move the statements directly on the fly, otherwise we just issue a warning to the user. And of course, then we insert back the dimension that we have abstracted, and we insert the directives if the user asked for it. The good things to have an automatic tool that does the transformation is that you can have specific option for different transformation, and you can try out different strategy really quickly. In a matter of few seconds, you can issue another code and try out if it's more performant than the other. For example, when you move to an accelerator and you use OpenACC directives with local arrays, you have different strategy. You can privatize them, so it means you will issue a copy of the arrays for each thread. But of course, you can also promote them, so you will have only one copy and then a unique index for each thread that will, like did not do a data race on it. For the data movement strategy, we have also option. We have an option that assumes that all data are present on the device already. So it means that you can directly use this approach in an already ported model where the guys have already put all the data on the GPU, and then you want just to put this physical parameterization as a single column abstraction, so the CLAW compiler will just assume that the data are present. If not, it can also generate the data movement for you, and then everything will work fine. And we have also some strategy for collapse sim loops or not, as it can result in different performance in different use cases. So once we have transformed this code, what are the performance that we can achieve? Well, just before, I want to show you what kind of output you can expect from our tool. So as you can see, this is the same example as before, but transformed for GPU with OpenACC. And as you can see, it's really well indented, it's human readable, and if you need it, you can even debug it because it doesn't look like assembly. So in terms of performance, we have some results done on Pittsdane on one node because we are interested in single node performance here. So the dark blue bar are the original code, which was a single core code with no OpenMP, no OpenACC, and with the horizontal dimension in. And if we take the fastest compiler, the Cray compiler as a reference, we have this performance, of course. Then we do a naive OpenMP implementation by hand. We just introduce some OpenMP, and we can get easily a factor of 3x of performance, which is not super nice because we are running on 12 core. We expect more, but we will see later that we can reach better performance. This is a handwritten performance. Of course, if we move our code to a single column abstraction, but we don't transform the code can be run still on the same domain size, but it's behaving badly in terms of performance. And this is easily understandable because here we have over 16,000 columns, and we call the subroutine once, so 16,000 times, where normally you will call it only once. So if we transform this code automatically with CLAW for a CPU target with OpenMP, we easily reach about 8x of performance compared to the original code. This was the result at the time of the paper. Now we have a little bit, we have increased a little bit the performance in the CPU backend, and we have 20% more performance in the latest version of the compiler. And then the nice thing is that in terms of performance portability, if you ask CLAW to apply a GPU loop structure but apply OpenMP as well, you will see that you get really poor performance. Now if we switch to the GPU, so this reference is the fastest OpenMP that I had on the previous slide, so the Cray with 8x of performance, and then we ask CLAW to generate a GPU target with OpenACC directive. And here we have, again, an 11x of speedup in terms of performance. So this is really nice. With PGI, we have a little bit less performance, about 20% less. Hopefully, they will catch up in the next release. So it's not so a problem at the moment. If we check out how we stand with an handwritten OpenACC version, we see that we are really on par. But the nice thing is that the unwritten version maybe takes weeks to a beginner to write, or several days at least to an expert. But here, it's just 2 seconds to transform the code. In terms of code metrics, 80% of the original code is kept. And actually, the 20% left is what we remove from the code. So we make it simpler because we remove do statements that the domain scientists don't really care about. And we demote arrays where we need to, and we just added 3 lines of code to instruct the CLAW compiler to do the transformation. This approach was also applied in the icon model, and we reach also exactly the same performance as an unwritten optimized version for OpenACC or OpenMP, CPU and GPU. So this was not only a research project, the CLAW compiler. We are still under development at the moment. We have a project called the ENIAC project, financed by the PASC initiative. So the goal is to enable icon model on heterogeneous architecture. Icon is the new global model from the DWD in Germany. So I have one colleague of mine who is porting it to OpenACC to have a baseline. The DICOR will probably investigate the use of the grid tool stencil library to do some of the computation of the DICOR. And of course, from my side, I'm looking at performance portability in the Fortran code. So we are enhancing the CLAW compiler, of course, with the modern Fortran. We are applying single column abstraction in some of the physical parameterization, and we are implementing backend for different hardware that we can run on today. So as I said, everything is open source. It's available anytime on GitHub, both for the OMNI compiler and the CLAW project. Everything, you can even test your code on the Travis CI, and you have some manual if you want to implement your own transformation. And as a summary, I would say that we have proved that we can reach performance portable code with a simpler code, actually. So there is little to no change in the previous code. You just make it simpler. So now the domain scientists can focus on their problem and not on the optimization for the architecture. Our approach is 100% standard Fortran, fully open source, and you can easily extend the CLAW compiler with anything else. So I would like to thank again all the co-authors of this paper. Some of them are here at the conference. And if you have any question, I will be glad to try to answer them if I have an answer.
Thank you very much. So we are open for questions.
How universal it is? I mean, we can apply to whatever code, whatever algorithms, I don't know. Is it explicit, implicit, matrices or something? Because you tested only on this one. Are you going to test on another codes? It's very interesting. I really admire what you're doing.
Well, at the moment, we test mainly on weather climate code. So the different model like COSMO model, ICON, we have some contact with ECMWF for IFS, collaborating with us. We have also some contact with people at STFC and Met Office. So we are trying this approach on different codes. And of course, it could maybe also be applied to different domains where you have single column abstraction, where you have no dependencies on the horizontal. But we tried only for weather and climate at the moment.
So OpenACC, maintaining OpenACC is a major headache, as you well know at Meteo Suisse, and Oli gave a very nice talk about this last week. Does this in any way fix this? Well, or you still face the OpenACC maintenance problem?
Well, we face the OpenACC maintenance everywhere where the code is not ported to single column abstraction, because there we don't perform data analysis or so on. But the code that you will ultimately push into your repository will have no directives, and then the tool, each time you make like a bug fix in the computation, it will reanalyze the code and issue new directives if it needs to. So I think it will help in this term to not have this problem.
So you're not maintaining the emitted code. Then that begs the question, why are you emitting in Fortran and OpenACC? Why are you not just emitting in C++ and CUDA?
Well, this is a good question. When we started the project, as it was really like a new project, scientists wanted to see the output code. So we had kind of one of the major requirements was that we need to generate something as close as possible to the original code. But now at Meteo Suisse, we are talking different approaches where we can materialize what we do in the optimization and maybe have a similar intermediate representation of the code and then generate something totally different, like grid tool code, like C++, like CUDA, or so on. So this will be in the next step.
Thank you.
You're welcome.
And very nice work. Yeah.
Thank you.
Time for one final question.
Here, please. My question had to do with once you've refactored the code, the numerical consistency that should be expected. And is there some kind of a check on that at compile time or source translation time?
Well, in the compiler itself, we don't check for that, but we have all our test cases have we use a library to serialize all the data, and then we can validate them. And so far, I mean, all the outputs are totally like validating.
Okay.
So it's if it's CPU, then it's same results, byte identical. Then GPU, of course, you have a bit difference compared to the CPU, but then we have a threshold like where it needs to be.
Very good. Thank you.
Thank you.